Many things, und das möchte ich sagen, vielen Dank für die Möglichkeit, einen Vortrag hier zu halten. Sehr angenehm indeed. And I would like first to start with an overview how we define motivic homotopy theory in the sense of Morel and Voevodsky, and then how to define a similar approach for non-unital algebras, just algebras, associative but without identity, and then how to make computations of stable homotopy type of associated spectra by using either Cuntz approach to Kasparov K-theory, to bivariant theory of locally convex algebras, and further extensions by Cortinas-Thom to all algebras, and respectively in the motivic situation how to compute the suspension spectrum of smooth algebraic varieties in terms of Voevodsky, in terms of frame correspondences of Voevodsky. So first of all, I recall that if K is a field, we work with smooth algebraic varieties over the fields, and well, there are plenty of models for unstable motivic homotopy theory, one of which is just denoted by M star, M for motivic spaces, just preshifts contravariant functors on smooth K to pointed simplicial sets. These are just contravariant functors, but of course we want to put a few relations here. This is we then put two relations. Namely, the first relation says that we want to see such arrows as weak equivalences in M star. And another collection of relations comes from the Misnevich topology, namely, for example, from Misnevich elementary squares, one of the models. So, namely, they come from pullback squares of Misnevich elementary squares of smooth algebraic varieties, and elementary, these are called elementary Misnevich squares. So, and namely, this should be an open embedding, a map from X prime to X is a Natal cover. This is a pullback such that on complements we have an isomorphism of closed substance with reduced structure. So, and I recall that the unstable motivic homotopy type of a variety is the homotopy type in this model structure M star modular these two relations. Well, I denote them by, say, relation A, relation B. So I'm not defining in full details what arrows come from B, but essentially these are fibrant objects must be section-wise fibrants with A1 invariant property and with Misnevich excision property. So one of the models. And the unstable homotopy type of a variety is the homotopy type of the pointed objects X plus in this category. Yeah, and well, then the next step is we want to compute the stable. Yes, please.
Silly question. So X plus, how do you view it as a sheaf?
X plus, okay. This is a Hom in smooth K, representable one, with added disjoint points.
So it's a discrete simplicial set?
Yeah, it's a constant simplicial set.
Okay.
But in algebras, there will always be the zeroth homomorphism. They are always pointed. The difference is, there is a difference with algebra. But with schemes, we just add a distinguished point and say a representable function. Yeah, and then we compute a stable homotopy type of the suspension P1 spectrum of X. And where P1 here is pointed at infinity. We regard it as a pointed constant simplicial pressure pointed at infinity.
What do you call the stable?
Yeah, just a second. Yeah. Whereby by stable category of P1 spectra, we mean, and denoted by this, we mean the stable model category of P1 spectra defined as usual, these are collections of objects in here of motivic spaces together with an action of P1, pointed P1, and structure monomorphisms. And there is a standard then procedure after many authors to define the stable model category of P1 spectra associated to the category M star.
You mean to take the slash product of N with P1?
Yeah. So an object here, an object here is a collection of motivic spaces together with structure maps like this. And of course, Homs of P1 spectra are defined as usual. So model category of P1 spectra associated with the category M star. In fact, modular A plus B, of course, because it is this category which is interesting. I'm not saying about S1 spectra here, but the right category stable motivic theory is that of, for example, of P1 spectra. Or when we invert both the simplicial circle S1 and the algebraic circle, which is the spectrum of Laurent polynomials, pointed at 1. There are plenty of models. Okay, and another category which is can be defined close to this one, if we start with a commutative ring here, And by K-algebras, we mean all non-unital algebras over K. Well, on purpose, I'm ignoring set theoretical issues because this is a large K-theory. But we, in practice, we take a reasonable small subcategory here, and this choice won't affect the major computations. Whenever you want to enlarge it, you can do this, not affecting the major computations.
So it's the category of smooth.
It is small,
That's small.
but this one is large. Yeah. Or for example, normally in C-star case, we take separable C-star algebras, which form a small category, and then we can carry on. But here I leave set theoretical issues because otherwise I don't have time to explain all of this here within an hour. And by denote by spaces on algebras, just functors, covariant functors. From algebras to pointed simplicial sets. And why do we consider covariant functors? Because, for example, if we deal with commutative algebras, then the functor of taking the spectrum is prime spectrum of a commutative ring is contravariant. So here we deal with contravariant functors, here we deal with covariant functors. And for any algebra A, we associate a space which is represented by A home in algebras from A to anything. But by the way, it is pointed at zeroth homomorphism. Yeah? Because we deal with non-unital algebras and non-unital homomorphisms. A major object here. And also, of course, what is the affine line here? Affine line is this representable object. Yeah. And I want to introduce two relations. Say relation A here. I take all homomorphisms from A to its polynomial, the usual homomorphism. So I put two relations. So this is an analog of this relation. A should not be confused with algebra, say B here.
Yeah, but then the next thing is only going to go B.
Sorry?
Are you going to put?
Sure. Okay. Okay. Should I? What is the? Forgot. Calligraphic A.
Okay.
Calligraphic A and calligraphic curly B. What is the relation here? Consider. In fact, this relation comes from the property for homotopy algebraic K-theory, which is A1 invariant, and also it is excessive under all pullbacks with under all pullbacks here are prime to say A, here B, B prime, and such that F is a surjective homomorphism. Yeah. But in fact, if you want to deal with Karubi-Villamayor, approach, there are so-called GL fibrations as well. And in fact, I'm not defining relations in most generality, but there are plenty of fibrations, reasonable fibrations, like all surjective homomorphisms, GL fibrations, but here we shall deal with F is split in as a homomorphism of K modules, which is very typical in Kasparov K-theory, for example. We consider extensions with split surjections on the right. But here we have homomorphisms which are K-split. Surjective, if K is a field, then every surjective is such. So, and this must be pulled back. And out of this we generate relation B. So we write RA here, next goes to RA prime, for example, RB prime. Yeah, we just swap all arrows in that diagram. So this is neither pullback or push out, this is just a square of representable objects. But we, out of this, with these two, by the way, monomorphisms as naive functions. And out of this we generate a relation. And let me denote as SPC on algebras, motivic as spaces.
What is the relation? How did I be? I don't understand.
This relation. Okay, I can explain in more details. Okay, I take push-outs.
Oh, sure.
Push-outs here. Push-outs. This time we get a corner X, which is not representable. This is just a naive pressure functor, and I want to invert this arrow, such arrows. And in fact, this also related to some work of Gersten in the 70s, to your works with Villamayor. So we are able to recover some of them. But in using the language of simplicial functors, well, we embed everything in this category and working there. So. And similarly here, by the way, for this, we take push-outs, it's a pressure, and we call these diagonal arrows weak equivalences, local weak equivalences. And modular A and B. Curly A, fortunately I forgot Gothic A. Gothic B is so close to this B. This one. Okay, curly A, curly B. So, and just in case, well, I call this motivic, there should not be any confusions with other theories, motivic approaches to non-commutative objects, like that of Taboada. If you are uncomfortable with this term, just remove it and let us refer to it as one of the reasons why I call the stable theory here, algebraic Kasparov K-theory, is that, well, motivic homotopy theory is normally known as, in terms of dejugative, it's after Taboada, and may confuse other people. And another motivation to call it algebraic Kasparov K-theory is that major computations are computed in terms of Cuntz approach and Cortinas-Thom approach to bivariant K-theory of locally convex or all algebras. So this is the name. But if you are not happy with it, just remove it and call it something. Let me within this hour, call it motivic, MOT. Yeah, and similarly, we define S1 spectra. This is important, not a kind of P1, S1 spectra, where S1 is the ordinary circle associated to this category. Yeah. Again, we take such sequences and take structure maps S1 smash xi to xi plus 1, such that and ordinary maps of S1 spectra.
So this is one is the simplicial one.
Simplicial, yeah, on the right hand side. Absolutely the same. So, or for example, if I was writing software code, yeah, just replace U, everything, and reverse arrows and put algebras. Nothing, just rewriting this definition. Nothing else. But instead, P1, I'm using S1 spectra associated to this model category. And the major object here, of course, is sigma infinity RA S1. Can we compute this? Yeah. It's homotopy type, stable homotopy type. By this I mean an explicit fibrant omega spectrum, which is in fact excessive. What is a fibrant object here? Excessive. A1 invariant or polynomially invariant. And in fact, it will be excessive in both variables. Yeah, and such that later we'll see that the computation will be denoted by this symbol, KAB. In fact, I'm writing here as a function. And this is an explicit omega spectrum, such that, for example, if A and B are equal to the field of complex numbers, I'm just wondering whether it is a model. And I'll justify why I'm hoping that this is the case. The usual suspension, the classical suspension spectrum. Not equal, I mean, here it's sim. Yeah. Has homotopy type of the classical sphere spectrum. If I deal with commutative C-algebras, in fact. But this is a question.
Usual sphere spectrum, topological.
Topological spectrum. Classical topological spectrum, yeah, sphere spectrum. Yeah.
Okay, KAB is a mapping spectrum in the stable category defined.
KAB is defined explicitly. I'll show how to define it. Yeah, in terms of operators J omega, which are very popular.
Your S1 spectra. I mean, your S1 spectra is a stable field category, or stable.
This is an S1 spectrum now.
Yeah, but how it's related to the mapping spectra in your category?
Mapping spectra.
You measure mapping.
Yeah, but I mean, okay, so you define this stable model category of S1 spectra?
Of S1 spectra,
which
yeah.
models in stable field category, which is mapping spectra. And then you can talk about map between suspension of RA, suspension of RB. And is this the same thing as KK or K of AB?
Later, yeah. In fact, one of the major theorems here is that the homostat in the homotopy category from one suspension A to another suspension B is, in fact, from B to A, because here is contravariant, everything is given by P naught of this spectrum. And this is in fact, I would say the major results. That we are able in the end to compute homostats in the homotopy category of spectra, not associated to this, but spectra will be denoted by SPC.
But then I'm confused. What is then this left bold-face K thing?
What is, sorry?
What is this K, the A, comma?
I'll explain later, just a second. I should say a few words about Cuntz formulas and Voevodsky's formulas, briefly. No, 27 minutes. It's fast. So I'll define it, yeah, a bit later. Just to define a framework in which I'm working. Now, let me write now here Cuntz formulas. So I'll be writing some symbols making no sense at the moment, just symbols, yeah. And then because we can substitute, we can replace them by C-star algebras, locally convex algebras, all algebras. I'm writing some symbols first. So namely, what is the formula? It is calling over K, JK, A, next curly K, depending where we are, a symbol box tensor product on purpose. Yeah, because in practice, this tensor product is specific to, say, C-star algebras, locally, everything. Next, SK, B, modular homotopy. Yeah, if I clearly remember. So, and here, denoted by star.
Curly A?
Curly K.
No, but A plus B plus
A2B01 on the interval.
It's a homotopy.
Modular relation, a polynomial homotopy, for example, in practice. So homotopy X cross, yeah, X cross A1, similar homotopy. Yeah, I'm writing just this relation. It's okay, homotopy. So on locally convex algebras, it is called diphotopy, or diphotopy, for example. Or, for example, on the level of all algebras, we replace this interval by polynomials, yeah, and then this is nothing but we equate polynomially homotopy, like in your paper with Villamayor, if I clearly remember. So this is just something. I mean, a collection of symbols. But if we work with locally convex algebras, then star is nothing but what we call KK small after Cuntz. Let me denote, although he denotes as by here, algebraic, but let me write locally convex algebras. Because the small kk will be reserved for another kk small on all algebras. AB here. Or, for example, if we work with C-star algebras, then star becomes kk capital of AB. Finally, if you work with all algebras, with algebras K, and curly K is the ring of all finite matrices, then and B interval is the algebra of polynomials, then we arrive at kk small AB of Cortinas-Thom. And of course, for locally convex algebras, one meaning of K, of curly K, for sister algebras, another meaning, as well as tensor product, as well as the operator J and S. Well, briefly, S is this algebra, and also it fits in an important short exact sequence. Cone of A is cone of B is B 0, 1 to B, onto B. Yeah, split extension.
What happens if you take the periodic numbers and you get something new?
Periodic numbers? Never dealt with periodic numbers. No.
Because you have an ultrametric topology.
Possibly. I never dealt with periodic numbers at all. And J, in fact, J is another important operator here. This is, in fact, a kind of sphere object on B, but J fits in an extension where T is the tensor algebra. It is contractible in practice. Here we've got A, here we've got cone, an extremely important extension here. And let me denote this arrow by sigma on purpose. I want for this hour. For this hour, because I'll justify this. And essentially, the colimit here is taken over sigma. And in practice, this sigma is a major motivic equivalence, gives a major motivic equivalence in this category, if you work with all algebras. So this sigma is very, very important. And in fact, it turns out that as soon as we invert this motivic equivalence, we'll compute all desired homotopy types. And this is the idea. Okay, and what else? In practice, if I should mention that KK locally convex algebras, KK small, or KK capital, etc. There are also E-theory, bivariants, many associated categories are all triangulated. After many authors, Meyer, Nest, Thom, Cortinas-Thom, I might have forgotten somebody. So they are all triangulated. And in our approach, we'll represent KK groups by spectra, but stabilized spectra. I'll define later what I mean by stabilized. Okay, and this is essentially an introduction to Cuntz formulas. Okay, and what about another approach? So, Voevodsky's formulas. I should say first that in practice, I will remove K, curly K, and just deal with J and S operators. I won't need K in general. Okay, let me denote by this symbol frame xy and bar, long bar, the following column. Column over K, frame K. These are just symbols at the moment. Modular, again, A1 relation, like here. And in fact, it's a result of Voevodsky that something here is computed what I want to write. Now I'll briefly define what is this. Home in pointed Misnevich shifts from x plus smash pointed P1 smash n times k times y plus smash t to k.
Yeah, that's without the colimit.
Colimits, colimits, thanks, colimits over k modulo a1. Yeah, where a1 in this variable. Yeah.
So is each term equal to each term in the colimit, or just the same in the
I have just written some symbols. Yeah, and when by frame k, just a second. Frame k xy is the set of level k framed correspondences.
Tk is a torus.
Sorry?
Tk is a torus.
Tk is ak over ak minus origin. Misnevich. I'll write shortly. Correspondences. And next, okay, what is Tk? Well, T1 is affine line over its Misnevich, not Brezhnev. And then Tk equals T smash Tk times, which can be computed as this Misnevich minus origin. X and Y are smooth varieties. Yeah? And, well...
So, exactly, I just asked, so,
yes, please.
I mean, if you write home this data, is it precise interpretation that you take by node of the mapping space in your category M star modulo A plus B, or is it really something else?
No symmetric. I don't take any symmetric space here. No.
Yes, it's a different.
Yeah, so I miscarried that.
I mean, you write home, so I don't really understand these symbols, but my interpretation would be you take the pi node of the mapping space in the category M star.
Okay, it is pi nodes. If I'll put it later, just later. Yeah, if I put the so-called algebraic delta here, turn it in the first variable. Turn it into a simplicial. This is a
No, I mean, not on this level. I mean, just if you define the category M star modulo A plus B on the other upper.
It is not mapping space. P-naught of mapping space. No,
it's not.
Mapping space is defined in terms of ordinary simplicial.
You really work with set value sheaves here.
This is a set. The set of this is Colin of Hom sets in this category of pointed shapes between certain Misnevich shapes modular A1 relation.
I mean, the question is, what does this modular A1 relation mean?
Okay, A1 relation is the same with this relation, yeah, where we identify this is functorial in both variables, yeah, and we take x cross A1.
The concordance, you mean?
Sorry?
Okay, I think
Just a second. And we, for example, we identify maps like as usual. Yeah.
So T1 is an analog of Laurent polynomials and TK.
It's not Laurent polynomials, no.
Because like A1 and A0, so.
But
It is A1 over Laurent polynomials.
Okay.
It is A1 over Laurent polynomials. It's a sheaf.
It's a suspension.
It's another type of the motivic sphere.
So it's P1 more or less, no?
Motivically, yeah. And in fact, there is a major motivic equivalence also denoted by sigma.
Oh.
I insist here, sigma. P1 cross x1 to T smash P1 smash x plus to T1 smash x plus. Absolutely the same. Okay, and frame K, in fact, frame K xy has a long geometric definition. Yeah, if you look at Voevodsky's notes, in fact, frame K are defined in terms of algebraic varieties. I don't have time I have it here, but I don't have time to write it down, otherwise my time will be over. So anyway, this part is defined in terms of geometry. This part is defined in terms of, well, in categorical terms. And the right-hand side is very close, if you ignore K here, is very close to this formula. Absolutely the same. If you replace, if by J we mean T, if by S we mean P1, yeah, the relation is the same, yeah, and...
But whereas in there is, I mean, the S is tensoring with someone.
Sure, and here we take smash.
Yeah, but the J is not of that form. Whereas here you have two smashes.
Okay, but in algebraic, in algebraic situation, for example, in your definition of KK small, if I clearly remember, you take the subdivision of the circle and form an int algebra, and then you tensor this int algebra K times.
Yeah.
Yeah. Is it not the same with?
Yeah, no, I mean J is of a different nature. J
sure
is not smashing,
in fact,
tensoring with anyone. Yeah.
Sure, and so of course, in fact, I'm writing here everything modular A1 homotopy, as well as here. There are of course differences. I'm just saying about visual similarities. Yeah, just take this set, frame bar, and it turns out it is a category. In fact, there is a more general category of Voevodsky, but here I'm writing this on purpose. Modular stable and modular A1. And by the way, colimits is taking over a typical motivic equivalence, which I denote by sigma x, is given by x plus smash P1 to x plus smash T. This is a typical motivic equivalence. And similarly, this sigma is a typical motivic equivalence in algebras or in simplicial functions. And the colimit is also taking over this sigma. Yeah, given a morphism here, we smash everything by T and then decompose it with this sigma. Okay, and this is how colimit is defined. And one of the theorems, for example, to illustrate, so if you take characteristic K of the field is 0, then frame kk, let me write kk. By k I mean spec of k. Oh, okay, points, another notation, points. Bar is Grothendieck of k. This computation is essentially due to Neshatov. This is a theorem of Neshatov. And in fact, the left-hand side is commutative monoids, and its Grothendieck group, yeah, is the right-hand side.
Looks like Morel.
I would say Grothendieck K-naught of these monoids.
What is Russian with Morel's theorem?
Just a second, I'm going to write it immediately. Of course, which is by Morel, so it is written here as well. Which is by Morel. We know that it is P0 naught of the motivic sphere. Yeah, a kind of, or more generally, one can recover Milnor-Vitz K-theory, which is a kind of the ring of motivic ring of integers here. Okay, and so, yeah, and there is a hope, for example, well, to compute this motivic sphere. And as an application, well, to compute, for example, the classical sphere spectrum in terms of framed correspondences, as an explicit S1 spectrum, which is omega fibrant in positive degrees, in the sense that, as usual, as in K-theory, the zeroth space is something, but only the first space is omega loop of the following space.
It looks like framed for Watson.
Sure. A far relative of it. Yeah, over complex numbers, one expects, if we go to analytical topology, analytical functions, blah, 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 one expects to recover Pontelli. Sure. Yeah. Okay. Next, so, and well, how to compute, how we define the relevant spectra here on the right-hand side. Now, very big. So first, let me start with a typical simplicial algebra, which is typical for both sides. It is the simplicial algebra taking n simplices with n simplices the following algebra. B delta n is polynomials in n plus 1 variables modular relation modular this relation. By the way, every such polynomial, every such algebra is isomorphic to polynomials in n variables, but this isomorphism does not respect simplicial structure. Next, for any pointed simplicial set, x capital, I denote by b delta of x is the mapping space of simplicial sets. This is a simplicial algebra again. Sorry? Simplicial algebra. Yeah, it's a simplicial algebra. Yeah, functions from x to this we can define addition, multiplication on values. Yeah, it is a simplicial algebra. Now, by this b delta, I will denote because of lack of symbols. Yeah, and but I don't want to introduce Gothic notation. let me write this B delta. In fact, it is a form. I subdivide. This is the following int algebra: B delta on X, B delta. Next, I subdivide X, and so forth. I just subdivide X, yeah, and form this int simplicial algebra. Belongs to simplicial algebra ints here. T. Next, for every, in particular, we define B delta omega n, which is B delta on S1 smash n times S1. Yeah. S1 is the ordinary simplicial cell. And for any definition, the unstable algebraic Kasparov K-theory space is now curly K, again lack of symbols, AB for two algebras. This is co-limits over K of Hom sets in int algebras from A to B, BBB, where am I? Column JK here, JK of A, B delta of omega n. Yeah.
Okay.
Sorry?
Plus K. What's the
K, omega K, sorry, omega K. Where the colimit here is again taking over the sigma. That sigma I have already defined above. Maybe there. Here. Next. And now the KK spectrum AB is defined, it consists of KAB as one spectrum, K, JAB, and so forth, where J grows. It turns out it is an omega spectrum, excessive in A and B, of course, polynomially invariant everything. But here the structure maps from this space to omega of this space is not only a weak equivalence but an isomorphism of simplicial sets. It's a genuine omega spectrum. Yeah. And also, well, we can equally define, well, if you speak about K theory, it makes sense to introduce matrices now. Well, to say something about matrices. Let me write K Maritza AB is the same spectrum where K theory spaces, we take unstable K theory spaces and take column in this variable over all matrices. Yeah, we stabilize this argument in matrices. And similarly, stable A, B, we take K Maritza A but M infinity B. K Maritza. Yeah, by the way, it is worth to mention that motivic counterpart of Maritza K-theory, bivariant K-theory, is that of the theory of K-motives we defined joint with Ivan Panin. And its counterpart is that of K-motives, the so-called K-motives of smooth algebraic varieties. And this is the stable, and using an amazing computation of Cortinas-Thom, one can say that it follows from all this computation plus Cortinas-Thom that K stable B is the spectrum KH of B, non-convex. It is KH of B. Yeah, one of the computations here. Okay, what about 3 minutes for framed spectrum? By the way, I have to mention that P0 of this spectrum computes homosets between suspension spectra of algebras in the end. So the subcategory in the associated triangulated category of spectra is a subcategory, moreover it is triangulated, and the homosets there are defined as P0 of such spectra. Yeah.
Why K-stable is not K-morph? It is the same.
No. No.
It's different.
Different. It seems at the first glance they're the same.
But I mean, that column is a column like that, right? It's a column because you mean the int algebra. If you write the column, that's M infinity. Yeah, I suppose that's what mine.
I put column here. I should have put it here outside K. Sorry. Of course, column here. Column here, of course. Otherwise, you get an infinity. Of course. Okay, and so. Theorem that the suspension spectrum joined with Ivan Panin, if we take a smooth variety over an infinite perfect field here, K is infinite perfect, and then sigma infinity P1 of the variety is motivically equivalent to a spectrum denoted by MP1 of X, defined as follows. It is stabilized in the sigma direction of delta algebraic. By algebraic delta, I mean spectrum of K delta. Yeah, as usual, cross dash, and here I've got X, next frame delta cross dash X cross T. In this definition, we just add a further function in the geometric description of frame correspondences, or we put a further t above y plus smash t to the power of k plus 1, where k is, we take a coordinate of a k. So because I don't have time to define it in details, this is next we take local, Misnevich local vibrant replacements only. Yeah, and the theorem that this is a positively vibrant. So my time is over, P1 spectrum. And in particular, as a corollary, I would finish with this corollary that if we take omega infinity P1, sigma infinity P1, of, for example, x plus smash P to the power of m positive, m is positive, then this is a motivic space evaluated at any field extension of K small, then this is the following simplicial set. It is frame delta. It is frame delta t to power m. Very explicit simplicial set. And let me stop here. Thank you. Because this theorem recovers some theorems of Morel, a theorem of Morel, after Neshtov as well. Yeah, and
there's no x unter
x plus smash t to the power of n. Thank you. Yeah, thank you. Yeah.
So, quick question?
I have the feeling that you can generalize this to ultrametric case, where you take a key as a periodic numbers, and then you have Cortinas-Thom theorem probably with KH. Is KH ultrametric?
Yeah, possibly. Yeah, possibly.
This was used by Thom at the time 10 and somebody else.
Okay, do we have universal extensions there? Because the main engine here is that of universal extensions, where we compute all.
With Wiener, we introduce convergent power series in the periodic numbers.
Okay.
So the delta part should be trivial. Now, I don't know about the J part, but probably you have J also.
Yeah, that's what he means by universal extensions, the T, and therefore the J.
Well, you can take the non-polynomial sign series and variables. I don't see.
I think the formalism should work. The question is more what properties the resulting theory has. Since he doesn't talk much about the stable version, it's not so relevant there, but the usual K-theories have some features like homotopy invariance, periodicity.
Yes.
Homotopy invariance is still built in here by definition.
By the way,
Periodicity, of course, is probably out of reach in the periodic numbers.
We don't talk about periodicity, but even in the algebraic context. So, no, the point is to have a map from JA to, sigma. But I believe JA makes sense in the ultrametric case as well.
Well,
if you, I should say that the main technique here, why these spectra are possible to compute, is because we have a good theory of universal extensions. If you have the same theory in what you are saying, then I would say that one can define similar spectra. But here on the left-hand side, we use
then you have to use
some parts.
You have to use rigid geometry or things like this.
Well, there are 4 papers to say this. Yeah? And it requires cancellation theorem, some comparing theorem, and also generalized Voevodsky's theorem on pressures with frame correspondences, homotopy invariant pressures with frame correspondences. Yeah. And having all of these, we can compute. And also, let me very briefly say what the sphere spectrum is here. Yeah. It also requires all of these results. You cannot skip any of steps, any. Also, it requires a theorem of Levin about SH over C, about the computation of the sphere spectrum as the realization of the motivic sphere spectrum gives you the ordinary sphere spectrum. In turn, it uses a theorem of Cuntz and Voevodsky about comparing ordinary homology with finite coefficients, and also a conjecture of Voevodsky about S0 of the sphere. It requires many computations, and in the end we can write it as follows. It, as Simplicial said, it is delta over C, everything. C here, by C I mean points, spec of C. Next, frame delta C S1, but by S1, if M is a finite set, yeah, I associate to it the following variety, M times, yeah, and S1 grows in the second variable. It's a variety like this for every syntax, and so forth. This is stably equivalent to this, for example, as an application of all this left-hand side business. Hopefully, the right-hand side KCC will give this spectrum, but not now.
Okay, so I suggest that if you have any more questions, you ask them for the coffee.
Yeah, thank you.